Hi, everyone. My name is Mark Donaldson, and welcome to the TMLS 2024. This is the last talk of the session. And I'm the founder and CEO of Quantuity Analytics. We make edge IoT smart sensors for the commercial trucking industry. We have a patent pending on that. Right now, we have Shagun Sodhani. He's a tech lead at Meta, and he's the tech lead at FAIR, AI Research at Meta, where he leads a team of researchers to train large-scale foundation models for developing neuromotor interfaces. His long-term research goal is to develop lifelong learning agents that can continuously improve as they make decisions in the real world. Shagun, take it away.
Thank you so much. Okay, is this loud enough? Awesome, thank you. Let's get into the business. We are here to talk about torch.func, which is basically a way to do functional transformations in PyTorch. Quick show of hand, who does not know about PyTorch? Okay, so I can skip this first slide and just jump into what is torch.func. So there are a couple of things which are difficult to do with PyTorch. For example, if you want to compute gradients for every single data point individually, that's hard to do. It is somewhat difficult to run model ensembles efficiently when you have a bunch of those models on the same machine. It's also difficult to do stuff like meta-learning with MAML-like algorithms. And then it's also a bit tricky to do things like Jacobians and Hessians. And it's totally fine if you don't know MAML and Jacobians and Hessians. That's totally cool. So how is torch.func trying to solve these problems? Well, it's trying to solve these problems by introducing a abstraction called as composable function transformations. It's a mouthful, so let's break it down. There are two parts to this composable function transforms. The first part is function transforms. What are function transforms? Function transforms are functions. Functions which take other functions as input and return another function as an output. You might have heard of them as being called as higher order functions or functors and stuff like that, but really functions which take a function, return a function, in the process transforming a function. So that's the easy bit. And if you're confused about where the hell is a function transform coming from and you think you have never used a function transform, think again. When you do something like, hey, I have a function, I want to take gradient of that function, you are doing a function transformation. The other example on the slide is VMAP, and we can ignore that for now. But basically the point is, we do use function transforms quite regularly without just realizing that this is what we are using here. So that's the first part of composable function transforms. The second part, which is the more fun part, is composable. So you can have two function transforms, and you can arbitrarily compose them together to have a new function transform. And it sort of makes sense, because if you have a function that takes a function's input, gives a function as output, and you have another function, you can combine them. So the base way PyTorch is solving all these problems is through this new module called as torch.func, which provides you composable function transforms. And we'll see a bunch of examples of how we can use these composable functional transforms to solve these specific problems. Now, let's take a step back. We are talking a lot about functions. Why do we care about functions? Now, I'm not here to give a pitch on functional programming, which I like quite a bit. But in general, when your abstractions can be written as pure functions, and we'll talk about what pure functions are, but when you can write it as pure functions, you can easily compose them. And pure functions are basically functions which have no side effects. So things like print. Prints have side effects. They do something on something outside the function. For example, write on a standard input. So print is not a pure function, but a function, let's say, which takes an x and returns x squared is likely a pure function if you're not doing logging and stuff. So anyway, the functional programming pitch out of the way. The benefit of having pure functions is that it makes it easier to compose them. And by default, most of the things that you use in PyTorch are stateful. They have some notion of state, and again, you might not realize that, but for example, when you use anything from nn.modules, that's a stateless thing. Sorry, that's a stateful thing, because it's internally tracking its state in terms of weights and biases and stuff like that. So torch.func would work better if there were functional aspects in PyTorch, which are sort of missing. And torch.func just makes it easier to make PyTorch objects more functional. And then once they are more functional, you can compose them and do a bunch of good things on top of them. If this is still a bit confusing, let's go through the specific examples, and then we can come back to this slide. And at any point, if things are not making sense, like what exactly is happening, just raise your hand. Happy to take questions in between. OK, so let's take the first example of composable higher order function, though in this case, we'll only talk about the higher order function bit. And the first function that we are talking about is called as VMAP. VMAP, ignore the V word for a minute. Map is a function, map is a common construct, but basically it's something that maps one thing to the other thing, right? So what VMAP does is it takes a function, which works on one example. So the function that you're passing as input to VMAP is a function that works on one sample, on one data point. And what VMAP does it magically makes that function work on a tensor, which is more than one dimensions. So really write a function which works on one sample, wrap it in VMAP, and you would have a function which works with more than one dimension. And the way you use it is, and we'll see an example on the next slide, but the way you use it is, let's say you had the func and you had the input that you wanted to pass to the function. Well, you first do VMAP of function, which gives you a new function. So this bit is a new function here. And then you just pass it the inputs as you would pass in a standard Python programming. Let's take a concrete example. So I have two randomly initialized tensors, x and y, and I'm computing their dot product, and that's trivial. Now, what if I have, instead of two randomly initialized vectors, I have to randomly initialize two-dimension matrices? I no longer can do torch.dot because torch.dot only works for vectors. So I'm screwed. Well, not really. I can write a for loop, and line number 4, 5, 6 shows that, sorry, line number 4 and 5 shows you that for loop. So I've got this x and y. I'm sort of indexing in the shape of x. I'm computing, so I'm taking every ith vector in x, taking its dot product with every ith vector in y, and then I'm putting it into this sort of x dot y tensor. And yeah, I have my dot product, but it's more work basically. It's not elegant. How does VMAP handle this? Well, VMAP says that you have this torch dot which works with a single sample. You put it into VMAP, and then you have a new function that I'm choosing to call as batch dot product, which basically means going to take a dot product between batches. And that's it. Now you have a function which works on batches instead of a single sample. And yes, this looks like a trivial example because you could have literally written down a for loop, but this is more elegant because this is more general. This is in no way tied to how torch dot is implemented. It's also much faster, much faster. I don't have those. I wanted to run that in a Colab notebook and stuff, but I was told I cannot access Google here. Anyway, if you run this and you profile this, you would notice that VMAP versions are much faster. So it's not just syntactic sugar, it's actually more performant. And here there's a simple asserting that both these values are exactly the same. Okay, so VMAP was one commonly used function. The other commonly used function is called as grad, which really, as the name suggests, takes a function as input, returns a function that would compute the gradient of func, and it's different than saying return the gradient at a particular point. It's a function. It's not computing it at a specific point. It can compute the gradient at an arbitrary point. And the cool thing is, since this is all composable, you can do grad of grad of grad and get the third order gradients. So for example, I've got a function sine of x, which I'm writing as sine underscore x, and then I want to compute the gradient of sine of x. So I take my function sine of x, and then I just pass it to grad, and now I have a new function which can take the gradient of x, which can take the gradient of sine of x. And I know that the gradient of sine of x is cos, so this is the analytical expression. But if I don't know that, if I don't want to compute that by hand and stuff like that, I can just use torch.func.grad. And you can do it as many times as you want. So you can do grad of grad or grad of grad of grad and stuff like that, and it's still going to work. And this is where the compositional aspect comes in. It's one thing to have a first order gradient, and now someone wants a fifth order gradient, and now are we going to have a specialized function for that? No, just call it 5 times and you're done. Okay, the other aspect of compositionality that comes into the picture is when we can compose two different functions together. So far I was showing an example where I was composing grad with grad, and I was doing grad of grad and things like those. Now I can also do grad of map, or map of grad, or sorry, grad of vmap or vmap of grad. Remember earlier I said that there's a problem in PyTorch that it's not trivial to compute per sample gradients. Now, how can we compute per sample gradients using a combination of vmap and grad? Does someone want to take a shot? Just someone wants to think about, because you have a function which computes sample for one thing, and now you have a function that can take something that works on one input and make it work across a batch of input. Does someone want to take a shot at how we can sort of combine these together? And you don't have to write code, right? No errors, nothing. Does someone want to take raise their hand, or maybe just say it out loud? Look, there are two options. Vmap of grad. Sorry? It's simpler than that. Yes. Should the order matter? Yes, the order would matter. And think of it this way. The order would matter because vmap, if you give it, vmap is going to take a function and make it work across multiple dimensions, right? So if you do grad of vmap, this means whatever is being passed to vmap has to be a function that already works across. Sorry, whatever is being passed to vmap has to be a function that works on only one sample. Versus if you do vmap of grad, you can pass whatever you want to pass to grad, right? So there's a little bit of nuance there. It's even simpler. This is not a maths class. We are programmers. We are lazy. Or what's the lazy way of? I mean, I look at it and I'll be like, look, there are only two options, right? Grad or vmap of grad, right? Like, and yes, there could be more sophisticated things, but maybe those are the things that I would start with. Now, this is a bit of a bigger example, so we'll break it down and we'll go through it step by step. So line number 1, I'm just doing my imports. Line number 3, I'm just setting a batch size and a feature size. I need to have a model. I need a model so that I can take gradients with respect to. Well, technically, I don't need a model. I just need a function with which I can take gradients, but just to keep things a bit more PyTorchy. Though you would note that the function that I'm using, the model that I'm using in line 5 is not really a model. It's just a W transpose X kind of a thing, right? It's not literally a linear, n dot linear or something. Anyway, so I've got a model of some sort, a linear model of some sort, and then I've got a function whose job is to compute the loss. So what this function is doing is this function is saying, oh, okay, I've got a bunch of weights. I've got an example, and I've got a target. So first I'm going to, in line number 9, I'm going to take the weights, pass them to the model, pass the example, and this is really doing W transpose X. It's a more fancy way of doing W transpose X. So I get a prediction from Y. And then I take this prediction, and I compute the mean squared loss with this target, which was given to me as part of the input. And that's it. So that's all I'm doing in the first 9 or 10 lines. Right? And then I'm just sort of instantiating weights and examples and targets by hand. Like that's all I'm doing. I could have done all of this with n dot linear, and we'll see an example later in a few slides where I would not do all these things by hand. So this is all I'm saying. All I'm doing. If at any point this is not obvious, if at any point it's like too much code, please raise your hand. We have plenty of time, and I would rather answer questions versus sort of go through the slides. So, okay, so we have got this thing now. Let's just go back one more time. So I have a function which can compute the loss, and the gradient is nothing but the grad of compute loss, right? So in line number 2, that's what I'm saying. I'm saying I have a function that computes the loss. So I'm going to pass it to grad, which is coming from functorch. And now I have a function which gives me the grad of loss. The nice part is whatever I was passing to loss, I can pass to grad of loss and get the gradient with respect to that. So that's the first bit. The second bit is now I want to do it per sample. Remember, this was working on a single sample. This was dot. Remember, dot does not work with batches. Dot only works with one sample, right? So anything that I was doing so far till line number 2 is going to work on a single sample. I want to make it work on a bunch of samples. I want to make it work on a batch of samples, and that's what I do here with vmap. So I take the grad of loss, pass it to vmap, and now I have a function which is going to compute grad of loss on every sample. And so it's going to return me a list where every element is replaced by the grad of loss. And that's what we do here. So the inputs that we would have passed to compute loss have now finally passed to this compose function in line number 5. And the grad weight, for example, is a tensor. Now, I know there are a lot of things happening here. Let's slow down a bit. Is it clear? Is it making sense? Or am I, yes? Indims equal to none, 0, 0. Exactly. None basically means that you don't need to broadcast across that. Yeah. So that's sort of like you have flexibility in terms of where you are broadcasting versus not, kind of a. 0 means for the examples, remember the input was, sorry, 1 second, just to make sure. Grad of loss, compute loss is taking 3 things as input. Yeah, sorry, the first example is, sorry, the first input is example. This means you're broadcasting along the 0th dimension of example. This is basically saying if you have 3 examples of shape 5, 5, 5, make a 3, 5 batch. Or assume that you are making a 3, 5 batch. You're not really making those batches. Okay, good so far? Okay, and again, if it's not obvious, it's pretty cool that you can do this grad on arbitrary PyTorch functions. You don't really have to. Sorry? Oh, yes, all of this is in documentation. Yes. This feature has been out for about 2 years now, so it's not like it's just that a lot of people don't know about it and don't use it. Just fine. Yeah, okay. grad plus vmap, this is what it looks like. Again, if this doesn't make sense, please raise your hand, because the further example, the more examples we're going to look, they are going to be more like this and a bit more complicated. So, okay, let's go to the next example. I said earlier that functional programming is good, and functions and pure functions have a lot of good aspects. And then I also said that most of the constructs in PyTorch are stateful. How do we reconcile this? Should we rewrite PyTorch? Should we, yeah, what's the way around? So functorch gives you this API called as functional call, which allows you to make a module which is stateful into a functional module which does not have state. And really the difference between a stateful module and a stateless module is when you do something like nn.linear, we know that nn.linear has a weight and a bias, but when you do nn.linear, you don't manage the weight and bias on your own. It's nn.linear manages it for you. Although you could have written nn.linear the way I'm writing it here, well, not exactly nn.linear, but without bias version of it, where I am managing the weights by my hand. So this is a pure function. Whereas when you do a forward call on an nn.linear module, that's, well, it's not a stateless function basically. So now the question is there a way for me to take a stateful object and make it stateless? And the reason we want to make it stateless is so that we can do all other fancy things that we have seen so far. And yes, there is a way to do that. And back in the day, I think 2017, 2018, 2019, when MAML was a very popular thing and a lot of people were doing meta learning, this was like a big request. It was like, how do we do this? We need a way to do this inner loop optimization stuff. Not a lot of people do it now, so probably a lot of people also don't know about MAML, which is fine. Okay, so how does the functional call thing work? Well, I've got an x and a x and t. I don't know why I called it t. It should be y. Sorry for that. Actually, I don't know why do I have a t. Y would be completed. Anyway, I have a randomly initialized tensor x. I have a standard nn.linear module that we are used to seeing. And then I'm getting the parameters of this module, so I'm extracting those. Well, extracting is wrong, but I'm just sort of fetching them in a separate params dictionary. And then I'm calling this functional underscore call. What this is doing is it's making the model stateless. So when I would call something with this model now, it would not be using the parameters of the model. It would be using this parameters that I am passing externally. And the cool thing about this is, again, you can arbitrarily pass parameters to the model, which is not trivial to do, or it's not straightforward to do it for more complex models. For trivial models like linear models, yes, it's really easy to do it, but as your models get more crazy and more stacked and stuff like that, it becomes more difficult to do these things. And in this case, I'm literally passing the same parameters to this functional call. It doesn't have to be just a convenience thing. Yes? Yeah. So stateless means when I typically do something like model of x, it is using the parameters of the model, right? But when, in this case, I'm calling functional underscore call, the model is not using its parameters. The model is using whatever parameters I'm passing here. In this example, I agree. I'm literally passing the same parameter, but that's more of a convenience thing because I wanted this example to run. Yes?
On the implementation of function calls, that because model would have all the named parameters as fields in the class, and then you're passing in overrides for it.
So can you please repeat the question? I think I will, yeah.
The model class, or the linear class,
Yeah.
having stateful parameters, attributes.
Yes.
And then when you're doing functional call, it's overriding.
Exactly. Yes. Yes. And you can imagine a bunch of places where this becomes problematic, and we'll talk of one of those places like batch norm. This is where things get a bit messy. That's in the caveat section of this talk. But again, it's pretty cool that this works by and large without any modifications. Yes? Yeah. Two examples. One is, again, algorithms like meta-learning, MAML, where you need to do these things. The more practical example which matters nowadays is if you had a model and you wanted to do things like, I want to compute the per sample gradient of it with a different set of weights versus the weights that the model has. Or when we'll see the ensemble example, you would see ensembles are much easier to do with something like this, because what would happen with an ensemble model is you would have one model with 10 different set of weights, right? So you do not want the model to use its own weights. You want the model to use the weights that you're externally providing. So in all these cases, it's useful to have a stateless model. And again, you can implement these things by hand for sure. The cool part is that it's sort of available. You don't even have to do that much work. It's, yeah. Yes?
So
Yes.
That's what you're doing.
Yes. Yes. Yes.
So
Yes.
because like keeping object states ultimately, leads to all sorts of awful memory issues, right? And Python memory special memory leaks and memory in general, right? Does this help us on that regard?
Actually, no. And the reason it does not help is because now it is saying you should manage that memory, right? I think the reason of doing this is different researchers, different use cases have different requirements. And I would even say that, look, object-oriented style probably fits 90% of the use cases. What about the remaining 10% or even the remaining 5%? If you talk to researchers who are doing optimization, like optimization researcher, they don't care about any of this. They want Hessians and Jacobians, and they want those things to be computed efficiently. So in a sense, this probably caters to a subset of the bigger PyTorch sort of user base. But the cool part is you can support that without having to explicitly break the workflow for everyone else. And all of this is now in PyTorch core. So it's not a separate library. When you do torch, when I call it torch.func, I mean from torch import func. So it used to be a separate library earlier, but I think a couple of years back it was merged back in. Yes.
Is the PyTorch, the torch.func package, is the whole idea to reduce side effects codes to allow further optimizations in the future? Because I guess like if once you remove side effects and everything and you have a functional paradigm, it is a higher level so that you have more room for optimizations. But I assume that maybe, yeah, what's the
There are parts where it helps, right? Like for example, writing a VMAP versus a for loop. A VMAP would be, depending on the size of the inputs and stuff, it can be orders of magnitude faster than writing a for loop. So it does give you those benefits, yes. But the primary use case again was enabling research, which is harder to do with an object-oriented style of managing these objects and managing the state and weight and stuff like that. Okay. And thank you so much for being a lively audience. This is great. So what are we doing here? Let me recall. So we have got a function, compute loss. I am passing the parameters to this. And yeah, I think this is basically the version where we compute the gradients of the weight. Yeah, it's basically the gradient of the weight per sample, I suppose, eventually, or something like that. I'm just trying to recall. But I don't think there's anything sort of very different happening here. OK, now we come to the ensembles. OK, what am I doing here? I'm saying I'm going to make 5 models. And for this example, I'm making 5 linear models. And not just linear models. I'm basically saying that I have 5 copies of a model. Each of them have different weights. And right now, line number 4 is really making them as different models. But in terms of abstraction, I'm saying I've got a model architecture, and I've got 5 different set of weights that I can be using. And the way I'm showing it in the code is by literally having 5 different models. Right? And now I want to do, and I want to use these 5 models as an ensemble. The naive approach of doing this would be to write a for loop. If you're more sort of itchy about the performance, you might want to push these 5 models on different GPUs and write your own sort of a little distributed program or something. The example that we are going to look here is how can I make this ensemble work sort of in an efficient way out of the box using the PyTorch APIs. But is this setup clear? I've got a bunch of examples that I want to pass through all the models in this ensemble, and the models in the ensemble are being shown in line number 4. And the restriction is all these models have the same architecture. They can have different weights for sure, but the architecture is the same. And we'll see why that restriction matters in a minute. So the way this is happening is I have a forward call. What this forward call is doing is this forward call is taking a set of parameters, some buffers. If your models have buffer, if they do not have buffer, that's cool. And the data on which you want to do, the forward call. And within this forward call function, you're calling the functional call function. You are passing models of 0. Now, this is interesting. We can do this because we know all the models have the exact same architecture. And it doesn't even have to be 0. It can be models of 1, 2, 3, 4. It doesn't really matter. It's just that you are providing the skeleton, you are providing the architecture. And then you're saying, I've got parameters and buffers. And yes, if you don't have buffers, you pass none and stuff like that. And then you're passing the data. So now the torch.func functional call is something that we have seen in the past. We know what it's doing. It's taking this model. It's taking this weights and buffers and parameters and stuff. And it's doing a forward call using the data object that is provided here. Right? Now, I have given you a way to compute this. I've given you a way to compute a prediction for one sample, where one sample is a model. one sample is not one sample of data. One sample is a model. Once we have something that works for one sample, how do we make it work across multiple samples? We VMap it. So we took this forward call function, we passed it through VMap, and now we have a VMap forward call, which is really just going to do a forward call, which is going to do a forward call across all the models for a given batch of data. Remember when I said VMap, the data doesn't necessarily have to be like, my point is you can make VMap across, across functions, which is what we are doing here. There's one piece which is missing, which is, wait, I've got a model, I've got a function, I've got everything, but I've got 5 copies of buffers. And if I've got 5 copies of parameters, how exactly am I stacking them together, right? Because sometimes these parameters would be nested dictionaries. They would not always be flattened tensors. So torch.func has this function called as stack module state, which is really just doing this boilerplate stuff for you. It's taking all the module states, concatenating them together and making a bigger sort of parameters and buffer object out for you. You could have done it by your hand, totally doable. It's just that, nested dictionaries, you have to handle a few edge cases by yourself. Stack underscore module underscore state does it for you. So by line number 7, line number 8, we are in a position where we have got a function which works over multiple models. We have got the parameters and the buffers also stacked up, and then we are just calling it. And the output is basically, the shape of the output is the number of models, the batch size, and the features, the output features, where every model would have given you batch size, out features. So this way, and none of this really depends on what the models is. Of course, there is the restriction that the models have to have the same architecture, but like I could have had a transformer architecture here, I could have had a crazy, like whatever crap I want, and it just works, and that's nice. Yes? Yes, I think it would throw an error because when you would try to do a forward pass through the model using inappropriately shaped parameters and buffers, it would just throw a regular error. Yes. There's no sort of. Right away. Yeah. Okay, cool. So this is all good. We can skip this, VJPs and JVPs. Let's skip that. I would just highlight 2 gotchas, and all these slides are available, so you don't also have to worry a lot about like taking notes and stuff. I think one gotcha is when you're using grad, be a bit careful about how PyTorch.nograd behaves with it. Depending on where you put the torch.nograd, the behavior would be slightly different. Again, it's in a slide, it's in the documentation, so let's not spend time there. And the second thing I want to highlight is, anytime you have a function which has side effects, it's going to be problematic. Sometimes it would be very loud problematic. Sometimes it would be a sort of silent problematic. It kind of works, but sometimes doesn't work. So be careful around that. VMap puts more restrictions. VMap does not allow you to do, in some cases, in-place operations and stuff like that. But by and large, it doesn't, at least for my use cases, the benefits of just having torch.func, because I can always write these things by my hand. But for a large number of cases, just using torch.func makes it simpler and is also more efficient, more proficient, more efficient in practice. Okay, this is the end. Thank you very much. You were a great audience. I love this.